Hello again, this is Dave Barry with ATI. Today I'm going to talk to you about X-ray diffraction and how we use that to understand what the structure of the metals we make are. The stainless steels, the nickels, the titaniums, the zirconiums, it's important we understand how they're made up and how they're structured to understand how to process them and what properties we're able to develop for our target applications. Structure, what's a metal? You look at it from our level and at eye level, and it's just a big block, right? What's maybe less evident is how it's composed of individual crystals of varying sizes. So in the industry, think about a computer hard drive. Every single bit of data storage on a computer hard drive is a collection of 65 to 100 individual grains. You want to store more on a hard drive, you have to make those grains smaller and smaller. So on a hard drive, a grain, being a single individual crystal of the metal, might be 4 or 5 nanometers across. Nanometer is a billionth of a meter, right? But then you look at your circuits and your chips, and those are put on silicon. It's very important in those chips that you have single crystals as much as you can. So you have whole ingots where you have one giant crystal where all the atoms are arranged very periodically and they're nearly perfect. And that's how you get good circuits. For our purposes, we tend to be kind of in the middle, right? We want to have relatively fine grains in our metal, not very large, but depending on the application, depending on what the target performance is, there's still a pretty broad range. Metals being crystals, being composed of lots of little crystals, how do we know what the structure and the arrangement of those atoms are? You can go all the way back to the early 1900s. Scientists were trying to figure out how things were put together, how the materials were. They didn't have these great microscopes that they could go and look at very, very small things of the order that we're talking about. And so they were looking for alternative ways to figure out how can I measure what they suspected to be the case but couldn't prove. And the discovery of X-rays, big part of it. The double slit experiment, really showing the wave character of light, another big part of it. Those are key things that went into what we use today to understand the structure of the materials we make, particularly the metals that we make here, and then how we can design processes to get different structures to make different properties. So the double slit experiment really was the original experiment that showed the wave character of light, right? When we talk about the wave character of light, as it applies here, light will interact with obstacles that have spacing similar to the wavelength of the light in a way where it'll scatter the light, and then because it's a wave, that scattering will coherently merge in some areas to form what looks like a unique pattern, randomly split through whatever the space is. It's not random. In the case of metals, it was discovered that X-rays have a wavelength that is very similar to what the atomic spacing of the different crystals are. And going back to the board, I'll show you how this works from a X-ray diffraction standpoint of materials. If we think about this, right, we have atoms and they're arranged throughout the structure and they're periodic, as I say. You know, if you're looking here, you see the same guys next to you. You look here, you see the same thing. So what's discovered is that as X-rays come in, right, they have a wavelength, they come in and they interact with the electrons of the individual atoms. That interaction gets that electron all excited, puts a lot of energy into it. What then happens is it vibrates and scatters out a new X-ray. But what's happening here is all of these are interacting with the incoming X-rays, and they scatter out X-rays back out of the structure, all over the place. So effectively what's happening with diffraction is that this guy is doing it, this guy is doing it, and as it aligns, where we have wavelength matching the period, we're getting amplification and coherency of that electromagnetic wave, and that's creating the signal that we can measure coming back out as the diffraction of the planes. So where you have set plane distances that align, we can then measure through a simple mathematical equation what the spacing of these atomic planes are versus the incoming wavelength. And that's defined by Bragg's law. So Bragg's law, very simple. Lambda equals 2d sine theta, right? So in this case, lambda, that's the wavelength of the light. D is this spacing between the crystal planes, and theta is the angle. So you have light coming in, and you have an angle going out. This is theta, right? So you can measure, because, and that's where the 2 comes from. You have theta coming in, theta coming out. It's 2 times the theta, and you get the equation, right? So this is the angle of the light coming off, and this is the spacing of the plane. X-rays of metals. There's a piece of equipment called an X-ray diffractometer that allows us to do this. We have the ability to do a similar experiment using visible light, in which we will use diffraction grating. A diffraction grating is a simple thing you can buy where it has, in this case, know what the number of lines, they're too small to see, but how many lines there are per millimeter that are in the wavelength range of light, of visible light. So what's important about this is we talk about wavelength, right? And we talk about angle and D. Wavelength in visible light and in lots of light is lots of wavelengths, right? You know, the sun comes in, it's the whole color spectrum. Those are all different wavelengths of light. In the case here, when we do X-ray diffraction, we actually make a monochromatic X-ray beam. If you want to do this test with a visible light diffractometer, then you have to pick a laser. A laser is a singular monochromatic light function that is generally known. So what we're going to do is we're going to go and we're going to show what happens and how you can visually see with this setup what you would not be able to visually see in an X-ray diffractometer, and we'll come back and we'll talk a little bit more about the math. So we moved to a darker room so I can demonstrate how this diffraction grating shows with the laser pointer that I have. And you see when I shine that through, what I have is the incident light is the big one in the center where there's no diffraction, but you can see the points off to each side which are diffracted from this laser, and that's the beginning of our pattern. Now we think about metals and crystal structure. What I've done here is I've taken 2 diffraction gratings and I've oriented them 90 degrees to each other, and we begin to get what looks like a cubic pattern here. So you can see again the incident down the center, but now I'm diffracting in both directions. If I get into the more complicated world, I can approximate that with a misaligned at an angle diffraction grating set. And as I do that, you see I no longer have a straight cubic looking diffraction pattern, but now I have a more complicated pattern that I can do the math on to figure out how those planes are oriented to each other and the distances related to this pattern. If I go to a smaller 1,000 lines per millimeter, so a smaller D in our equation, I get a much larger diffraction pattern so that my dots are much farther apart. And that makes sense. We have the same wavelength, so if I have a smaller D, I have to have a larger angle to make the same wavelength. So we're back from our experiment. So what did we see, right? Essentially what we saw was we had our diffraction grating here, and we were shining light through the front. And then on the screen, we saw the light shine straight through, right? So there's no diffraction there. That's just the light passing through. It's not interacting with the diffraction grating. But then we saw other dots, right, in each direction. And you saw, and I have it sideways here, but you saw when I put one diffraction grating this way and one diffraction grating this way, I got a grid, right? And that's because you have diffraction going both ways. Now, we go back to our equation. Lambda equals 2d sine theta. You want to test this at home. You have your angle here. Here's your theta. You have your d, which is the diffraction grating spacing, and you have your lambda here for the wavelength of light. So if you know what your diffraction grating is, you can calculate what your laser wavelength is. If you know what your laser wavelength is, you can calculate your diffraction grating. But effectively, what we're doing when we do an X-ray diffractometer is the same setup, except we're rotating and we're bringing in the light here, and then we are moving our detector across this spectrum. And the reason we're doing that is as we keep this stationary within reference to the light wave, then we have an ability to scroll through all of the different crystal orientations, and then we scan at 2 times the angle on the detector, and we can get a full picture of what's happening for all of the different structures in the metal. When we think about what our metal structure is, There are lots of different structures, and we designed them and used them for very specific purposes. Some are very simple. There's face-centered cubic structure. In the terms of what we make, we generally call that austenitic. A face-centered cubic structure is a cube with an atom on each face of the cube in each corner. There's body-centered cubic structures. Imagine a cube and you have one atom in the middle. The body-centered cubic structure we call ferritic, or in the case of titanium, we have a hexagonal structure, so they're not cubic anymore. They're actually in the shape of a hexagon, but they're not even in each direction. The base looks like a hexagon, whereas the vertical direction in this simple crystal looks more like a cube. Really high-strength titanium alloys, we actually have a mixture in the structure of hexagonal and body-centered cubic. And so ultimately, as material scientists and metallurgists, it's playing through the elemental additions we can add that create different structures and the processing we can do to create different structures to make the properties that we want in the final product.